Welcome to the video for tutorial 9. Since some of you did not have a tutorial session last week because of the public holiday, we will be covering problems from the actual tutorial instead of just covering problems similar to the tutorial in this week's video. So, let's start with number 1 from the TUT under procedure exercises. It says, show that the critical numbers of f of x, where it equals x to the 4 multiplied by x minus 1 cubed, are 0 and 1. What does the second derivative test tell you about the behavior of f at these values? Well, we know that when we determine the critical numbers, we need to look at the derivative of a function. So I'm going to work out the derivative of f, and if you work out the derivative, and I'm not going to do all of the steps to get there, you will end up with x cubed, x minus 1 squared, 7x minus 4. So what are the two things we have to look at to find our critical numbers? Firstly, we have to find where the derivative does not exist. So this derivative exists everywhere, so that's not applicable. The second thing we have to look at is where's the derivative equal to 0. So the derivative equals 0. This means that x has to be 0, x has to be 1, or x has to be 4 over 7. So in the question, it said to show that the critical numbers are 0 and 1. However, there is another critical number in this case, which is 4 over 7. The second part of the question asks, what does the second derivative test tell you about the behavior of f at these values? So what we want to do now is we want to work out the second derivative firstly. So let's just quickly do that. I'm going to do that by taking this as my first function, and this is my second function, and then applying the product rule. When I look at my first function, however, it is a product as well, so I'm going to have to use a second product rule for that one when I differentiate. So the derivative here is going to be the first multiplied by the derivative of the second, which is just 7, plus, now I'm going to work out the derivative of the first. But the first, as I said, is also a product. So for the first, I'm going to use another product rule. So I'm going to say I have x cubed multiplied by the derivative of x minus 1 squared, which is 2x minus 1. And then I have plus the derivative of the first, which is 3x squared, multiplied by the second, which is x minus 1 squared. And all of this has to be multiplied by our original second function. Then we can multiply the second brackets out. So we have x cubed, x minus 1 squared, and I'm just going to write the 7 in front here. Then I have plus 2x cubed, x minus 1, 7x minus 4, plus 3x squared, x minus 1 squared, 7x minus 4. I'm going to take out a common factor from all of these terms of x squared multiplied by x minus 1. And then I have 7x multiplied by x minus 1 plus 2x multiplied by 7x minus 4 plus 3 x minus 1 multiplied by 7x minus 4. So, from here we can now see that the second derivative at our first critical value, which is 0, will just be 0. Because if we substitute 0 in here, it's going to cause the second derivative to be 0. F's second derivative at our second critical value, which is 1, will also be 0. If we substitute 0 in there, it will just cause our second derivative to be 0. So these are both 0. That means that the second derivative test gives no information for x equals 0 or x equals 1. Now we want to look at the second derivative at 4 over 7. If we substitute that into this equation, then we get 4 over 7 squared, 4 over 7 minus 1, then we get 7 multiplied by 4 over 7 multiplied by 4 over 7 minus 1, and then plus 0, which gives us 4 over 7 squared multiplied by minus 3 over 7 multiplied by 4 multiplied by minus 3 over 7. So we have a positive and a positive and a negative and a negative. So the entire thing is going to be positive. And if the second derivative at a value is positive, what does that say about the original function at that value? Well, it means that there's a local minimum at x equals 4 over 7. That's the end of the first problem. The next problem says if f of theta equals 2 cos theta plus cos squared theta, verify the following on the interval, the closed interval from 0 to 2 pi. A says f is decreasing on the open interval from 0 to pi. To know whether a function is increasing or decreasing, we have to determine our first derivative. So I'm going to look at my first derivative, and if you work that out, once again I'm not going to write all of the steps, but you end up with f's derivative equals minus 2 sin theta 1 plus cos theta. So what we want to do is we want to find where this derivative is positive and where it is negative. Where it is negative, we know that it is decreasing. Where it's positive, we know that it is increasing. So let's just quickly look at sin theta between 0 and 2 pi. That's how that function looks, right? 0, pi, 2 pi, and then 1 plus cos theta will look like this. So we can see that 1 plus cos theta is always greater than or equal to 0. It's equal to 0 only when theta equals pi. And we can see that sin theta is positive between 0 and pi and negative between pi and 2 pi. So when we look at this function, we know it's going to be equal to 0 when either sin of theta equals 0 or 1 plus cos theta equals 0. So that's going to be at the values 0, pi, and 2 pi. So the first thing I'm going to write down is the derivative of theta equals 0 if and only if theta equals 0, pi, and 2 pi. Next, the derivative will be greater than 0 if and only if. So that's going to be when this gives us a negative value, because then we have a negative and a negative and a positive. So that's going to be when theta is between pi and 2 pi. And the derivative will be less than 0 if and only if theta is between 0 and pi, because then this will be positive, so we'll have a negative times a positive times a positive, which gives us a negative. What this means is that f is increasing on the open interval from pi to 2 pi and decreasing on the open interval from 0 to pi. Part B says we have to show that f obtains a local minimum at pi. So since we have a critical value at pi, why do we have a critical value at pi? Well, the first derivative equals 0 when theta equals pi, and the first derivative switches signs at pi. It goes from being negative to being positive. And that means that we have a local minimum value at pi. So by having shown that the first derivative switches signs at pi and it goes from being negative to being positive, that means that we have a local minimum at that point. So we've basically already shown that. So f at pi will be minus 1, and it's a local minimum. And then the last part of the question says, show that f is concave down on the interval from 0 to pi over 3. So what you have to do at number C is you have to work out the second derivative, which after simplification is minus 2 cos theta minus 1 multiplied by cos theta plus 1. So what you have to do is you have to look at where is your second derivative less than 0, because that is where your function, original function, will be concave down. So if we were to look at where it equals 0, well, if we just look at this part of the second derivative, we know that that will always be negative except when theta equals pi. So to determine where this entire second derivative is negative, all we have to look at is this part here, because this sign will then determine whether the entire thing is positive or negative. So, to determine where the second derivative is less than 0, we just have to work out where this is greater than 0. So, 2 cos theta minus 1 is greater than 0, which means cos theta is greater than a half. And that implies that if we look at the interval we are working with, theta is between 0 and pi over 3, or it's between 5 pi over 3 and 2 pi. So we have shown what we wanted to show. We've shown that the second derivative is less than 0 on the open interval from 0 to pi over 3. Number 3 says, suppose that 3 is less than or equal to the derivative of f, which is less than or equal to 5 for all real x. Show that 18 is less than or equal to f of 8 minus f of 2, which is less than or equal to 30. So, we are going to use a theorem here. Which theorem? Well, we will use the mean value theorem. So, we're going to start off by saying that if 3 is less than or equal to f's derivative of x, which is less than or equal to 5 for all x, then by the mean value theorem, f of 8 minus f of 2 must be equal to f's derivative at c multiplied by 8 minus 2 for some c in the closed interval to 8. That is just exactly what the mean value theorem says. And why am I using 8 and 2? Well, that is what I want to show lies between 18 and 30. So that's where I came to these values. Now, I know that I can use the mean value theorem. Why? I know I can use it because f is differentiable for all x, and therefore it's differentiable on the open interval from 2 to 8, and it's also continuous on the closed interval from 2 to 8. Therefore, the hypothesis for the mean value theorem are satisfied. Now, this, I'm just going to write here. So I have f of 8 minus f of 2 equals 6 times the derivative of f at c. I also have 3 is less than or equal to f's derivative at c, since c is just some value in the interval that we're working on, which is less than or equal to 5. If I now multiply through by 6, I get 18 is less than or equal to 6 times f's derivative at c, which is less than or equal to 30. And this is equal to f of 8 minus f of 2. So I can substitute it in here, then I have 18 is less than or equal to f of 8 minus f of 2, which is less than or equal to 30, and that's what I wanted to show.